Hello, my name is Jim Olson, and this is a number theory video on divisibility and the division algorithm. It may be one of the most important videos of the entire course because we have the definition of divisibility. This is not a hard definition, but it is a little bit different than what we might be used to, and it's something we're going to be using over and over throughout the course. So the definition will grow on you a little bit as we go. The first thing I'd like to do is look at this conceptually and base it in elementary mathematics, and then we will go to the formal notation. So we're going to be expressing division as multiplication and vice versa. We will first of all look at the case where the number does divide evenly into the other number. In other words, the remainder is 0. So let's say we wanted 57 divided by 3 using long division. We do the long division, we see that we get a quotient of 19 and the remainder is 0. Now, very important is how we check it. And this isn't just important because it's a check, but it's also the relationship between multiplication and division. So here's the check. We take 3 times 19, and that equals 57. And it does check, but the important thing is expressing the division statement as a multiplication. In general, what we're going to do here is take a number x divided by d, d is our divisor, and we're going to get a quotient up here. So we have x divided by d equals the quotient. And if we think about this as multiplication, x is equal to d times q. Our x is equal to the divisor times the quotient. We will often be writing this d times q equals x, and this is just using the symmetric property of equality. The notation we're going to be having here in the book, I'm going to be having d, and it's going to be dividing evenly into x. And this is true if and only if there's a quotient, dq equals x. And we'll see this formally in a few minutes. Now let's take a look and see what happens if it does not divide evenly and there is a non-zero remainder. For example, 56 divided by 3. Let's do the long division. If we do the long division, we get a quotient of 18 and a remainder of 2. How does the check work on this? We take 18 times 3, that gives us 54. And then we take 54 and we add our remainder, and that should give me the dividend, which is 56. Written out, this means that 56 is equal to 3 times 18 plus 2. In general, if I have A divided by B, and I get a quotient with the remainder of R, it means my letter A is equal to B times Q plus R. And this is a statement of the division algorithm, which we're going to be seeing formally in our textbook. This is the idea conceptually. In this video, we're looking at section 1.3 in our textbook, which is on page 13. Here we have a statement of the definition of divisibility. This definition is pretty good, but we're going to have an alternate form that is slightly better for a couple of reasons. If a and b are integers such that a does not equal 0, we say that a divides b if there exists an integer k such that b equals ka. And you might want to pause the video and read that over again to yourself. Continuing here in our textbook, if a divides b, we also say that a is a factor of b, or b is a multiple of a. This is the vertical line. This is not the slash. If A doesn't divide B, we say A does not divide B with a mark through the divide sign. 2 divides 4 is true, 7 divides 63, 5 does not divide 26. What I'd like to do now is state an alternate definition to divisibility. I would like you to write down this definition of divisibility. It is pretty well equivalent to the previous definition. Given that A and B are integers, A divides B if and only if there exists an integer k such that AK equals B. First of all, most definitions do need to be if and only if. What that means is that the condition on the left is A divides B. If and only if the condition on the right, there exists an integer k such that AK equals B. If and only if means we have the implication both ways. If we know the blue condition is true, then we can conclude that there exists an integer k such that AK equals B. On the other hand, if we know the yellow statement, that we have a situation where A times an integer k equals B, our conclusion can be A divides B. This is one of the most important concepts in the entire course, so you may want to pause and rewind the video a couple of times. This is a 3-star definition. Here's the definition of even and odd numbers, and I will let you look at that. We are going to be doing even and odd numbers later on in the course. This statement B here, this upside down A means for all. For all integers A, one has A divide 0. Any integer divides 0, and that's going to be one of our practice problems. Let's look at theorem 3. If A, B, and C are integers such that A divides B and B divides C, then A divides C. Let's prove this. Please take the following problem down in your notes. Here's what we're trying to prove. If A, B, and C are integers such that A divides B and B divides C, then A divides C. And I encourage you to look at our handout on suggestions for proofs. The first thing is when you're writing a proof, please write the word proof. Everything up to the comma is the premise. This is our given information. It's our information that we can use. We know that A divides B. What this means is, using our definition of divisibility, there exists k in the integers such that A times k equals B. And now we're going to do the same thing with the B divides C. See if you can write down what B divides C means. The definition of divisibility tells us that if we know that B divides C, there exists some number L in the integers such that BL equals C. Now I'm going to combine our two statements by using substitution. In the most recent equation, I'm going to remove B and I'm going to put A times K in its place. This is the substitution property of equality. But if you notice here, I have A times a number. integer multiplication is closed. What that means is that if k is an integer and L is an integer, k times L is an integer. So we have A times an integer equals C, and I can conclude that A divides C. So I have used the definition of divisibility 3 times. I used it twice in one direction, and I used it in the reverse direction. Notice that in our proof, the last line of our proof is in fact what we were trying to prove. This is the end of the proof. This is the mic drop. Have a cup of coffee. You might look at the proof that is written in the textbook here. It's quite similar to my proof. They used K1 and K2, which is fine. I used K and L. Also, they had the equation flipped, but since equality is symmetric, it doesn't make any difference. An example of transitivity is, since we know that 6 divides 18 and 18 divides 36, 6 divides 36. If this is obvious to you, that's a good sign. Theorem 3 is a 2-star theorem, and we might write down that this is transitivity. Now I'd like to go to theorem 3, which is a 3-star theorem. We have some integers here, A, B, C, M, and N. We also know that C divides A and C divides B. Then C divides the quantity MA plus NB. So we have a common divisor. C not only divides into A, but C also divides into B. This MA plus NB is called a linear combination of A and B. You want to make sure to write this down in your notes. Linear combination of A and B. We're going to be using linear combinations throughout this course. Let's go ahead and read the proof. Notice that they start with the given information. The given information is the if clause. C divides A and C divides B. There exist integers K1 and K2 such that C times K1 equals A and C times K2 equals B. Then what we do, they've kind of left out one step here. Maybe I will add one step in here. If we take our first equation here and multiply both sides by M, we get MA equals MK1C. Similarly, if we take the second equation and multiply both sides by N, we get NB equals NK2C. Then if we add these two equations together, we get MA plus NB on the left side of the equal sign, and on the right-hand side, we get MK1C plus NK2C. And we see that we have a common factor which we can factor out front, C, by the distributive property. So what we have here is C times a number equals a number. And we go back to our definition of divides, or definition of divisibility. This means that C divides evenly into MA plus NB. This definition of divisibility is one that's going to be growing on you gradually throughout this section and throughout the course. This idea of a linear combination can be combined with many, many terms. We usually just do it with two. Now we're ready for the division algorithm. The division algorithm is for when generally we divide and we get a remainder. Let's read the division algorithm carefully. If A and B are integers, such that B is not 0, in fact, B is a positive number. And the reason that B needs to be a positive number is it's the number we're dividing by, and you can't divide by 0. Then there exist unique integers Q and R. And as you can well imagine, Q is our quotient and R is our remainder. A is equal to BQ plus R, where R is greater than or equal to 0 and R is less than B. This is a power pack statement, and you may want to read it to yourself 2 or 3 times. Notice that the remainder must be less than the divisor. Just like in elementary school, the remainder must be less than the divisor. A is equal to BQ plus R. Very important thing, and we call this the division algorithm. Now I'd like to do a couple of examples so that you can see some of this in action. Let's do number 8. Show that if m is an integer, then 3 divides m cubed minus m. Let's get a piece of paper. So we're trying to prove the following statement. If m is an integer, then 3 divides m cubed minus m. Now, oftentimes it's a good idea to think about what this might be with some examples. Let's say that m is 5. 5 cubed minus 5 would be 125 minus 5, which is 120, and 3 does divide evenly into that. If m is 4, we have 64 minus 4, which is 60, and 3 does divide 60. So it's a good idea to make sure that you're trying to prove something that's true. You should start out your proof by stating the fact that you're doing a proof. Now, what I need to look at here is m cubed minus m. Well, the first thing I notice is that there's a greatest common factor. And if I factor out the greatest common factor, I have m times the quantity m squared minus 1. Well, that's the difference of squares. So we have m times m minus 1 times m plus 1. If you're a little bit rusty on your factoring, you're going to be able to practice your factoring a little bit in this course. So m cubed minus m, interestingly enough, is m times m minus 1 times m plus 1. So for example, if m was 10, we'd have 9 times 10 times 11. If m is 5, we have 4 times 5 times 6. So m minus 1, m, and m plus 1 are 3 consecutive integers. For example, 15, 16, 17, 106, 107, 108. Whenever you have 3 consecutive integers, the number 3 must divide one of the 3. 3 must divide one of the 3. Therefore, 3 divides the product. But our product is m cubed minus m. And this is what I'm trying to prove. So I am done. Now, the way the author does it, when his proofs are done, he puts a box. I will not require you to make a box when you do your proof, but the last line of your proof needs to be the conclusion, which is the then clause. I'd like to make a couple of obvious statements. 2 divides 10. Also, 2 divides 2. Proof. If A is an integer, then A divides A. This is pretty much a one-line proof because A times 1 equals A. And if you have A times something equals something else, that means that A divides A. This is using our definition of divisibility. Now, a bigger number cannot divide a smaller number. 8 does not divide 2. Now I would like to do number 12 as an example. If A divides B and B divides A going the other way, then A is equal to plus or minus B. You might try some number examples. What we're trying to prove is that if A and B are integers, A divides B and B divides A, then A must equal plus or minus B. Remember, when we're talking about integers, we are going to be allowing negative numbers. There won't be any decimals or fractions, but we will allow negative numbers. So, follow our nose. A divides B, and we're going to apply our definition of divisibility. There exists a number, I think I'll use X this time, which is an integer, such that AX equals B. In a similar manner, if B divides A, there exists Y in the integers such that BY equals A. You might try to anticipate what we're going to do next. What we're going to do is substitute, and in the second equation, I'm going to remove B and put AX in its place. Anticipate what we're going to do next. I'm going to divide both sides by A, and this means that XY equals 1. Well, X and Y are integers. We stated above that they're integers. The only way to have two integers multiplied together to get 1 is that they have to be plus or minus 1. This implies that X and Y equal plus or minus 1. Notice I have a comma between this. X equals positive 1 or negative 1, and Y equals positive 1 or negative 1. To finish this proof, I'm going to take two cases. Case 1, I'm going to have Y be positive 1. If Y is positive 1, then A equals B times 1, so A equals B. I'm happy about that. That was one of my possible conclusions. The second case is Y might be negative 1. If that's the case, A is equal to B times negative 1, which means A is equal to the opposite of B. My final conclusion then is that A is equal to plus or minus B. And this is, in fact, what we were trying to prove. So the definition of divisibility is one that we're going to be using much in this course, and it's going to take a little while to get the hang of it. But that's true about most things that we need to learn. This has been a video on divisibility and the division algorithm. Good luck on the homework. Have a great day.